All right. I will begin with a word of prayer. I will begin. Dear Father, we thank you for this day again, Lord. Thank you for the students. Pray you help us to use this time wisely, just to wrap up any questions we still have about differential equations, how to solve them, and so forth. And just pray for us to be able to think clearly despite the insane heat in this room. Amen. Oy, oy, oy. What was that? Do we have a final exam study? The whole semester was a final exam study session. In fact, well, I mean, it's a comprehensive final, so, you know. But no, I don't have anything specific planned, not ignoring your question for a second. But we have today and tomorrow, so we can talk about it now. After we talk about, of course, the remaining differential equations. Tell you what, let's wrap up any questions we have about differential equations today. We'll leave all of tomorrow for just talking about old tests, okay? Yeah.
Can I, 6.1, number 4.9, question about?
6.1, number 49.
Is it? Oh, it's number 49, I'm sorry.
So let me see, let me write this one out here. We've got dy dx equal to, what is it, x times the square root of x minus 6, and we're supposed to find the general solution, right? All right. So here, what I would do, what section was this again?
6.1.
Okay, so this is pretty much, I mean, so dy is, I kind of like to do, I mean, I don't know, you don't have to do it this way, but I think it's fun to still look at as separation variables. And so, of course, the integral over here is, well, that one I can do. And on the other hand, we have the integral of x times the square root of x minus 6 dx. No. Oh, no. Just do, just a u substitution will do it here. So what do we make u equal? Make u equal to this, right? And then, so u equals to x minus 6. What's that make x equal to? U plus 6. What's dx? Dx is du. And so you see what we have is the integral of u plus 6 times the square root of u du. Let's do some exponent laws. That's u to the 3/2 plus 6 u to the 1/2, why not? So this is 2/5 u to the 5/2 plus 6 times 2/3 u to the 3/2 plus a constant, which gives us 2/5 what am I u? X minus 6 to the 5/2 power, what's 12 over 3 plus 4 x minus 6 to the 3/2 power plus a constant. And there you go, y equals to that. That's my, now of course if this is an odd problem, you know, the answer in the back of the book might be simplified perhaps, but this is a good answer.
So, say if I use integration by parts, do you think that I would still pull away with the correct answer?
Well, I mean, how would we do integration by parts here?
Maybe ux, and then, ux, and then dv, square root of x. Okay.
All right.
6.
So we got, what's v then?
V is going to be, I got 2/3 x subtract 6 to the 3, yeah.
Okay. So that will give me x times 2/3 x minus 6 to the 3/2 minus the integral of 2/3 x minus 6 to the 3/2 dx rather. Yeah. I was just skeptical that you could get through the integral. Oh, wait a minute.
No,
Well, no, I think it's okay. So this is 2/3 x times x minus 6 to the 3/2 minus 2/3 times 2/5, I think, x minus 6 to the 5/2 plus a constant.
yeah, that's what I got.
Where's that extra x go?
Well, I mean, the question is, are these actually different? Yeah. Let's see here. So to convert this, I suppose what I would do here is that's 2/3 x minus 6 plus 6 times x minus 6 to the 3/2. I'm trying to rewrite it in the format of the other one. Minus 4 over 15, is it? X minus 6 to the 5/2. So you notice that I get this times that gives me another x to the 5/2. So I get 2/3 minus 4/15 x minus 6 to the 5/2 plus 2 times 6 over 3 x minus 6 to the 3/2. Now, oh, check it out. I've got my 4. You know, look at the see that is that. And if 2/5 is equal to 2/3 minus 4/15, we're in business. This is 10 minus 4 over 15, which is what? 6 over 15, which is 3 times 2 over 3 times 5, which is 2/5. Yeah. So we don't disagree. But this is good. It reminds us that when we use different integration techniques, we can get really different looking answers that may, in fact, be the same answer. Now, it didn't have to be that these were exactly equal. It could have come out that my constant and your constant weren't the same. If the constant had differed by 2, it would still be the same antiderivative. Excuse me. Other questions? Let's go on. Yeah. Can I erase? Probably should ask me about an integrating factor problem, yeah? We could look at more of those. Is there one you guys like to look at? Here, I'll try number 8. Did I do that one yet? I don't. What's that? So here we've got y prime plus 2xy equal to 10x. I'm supposed to solve this thing. All right, I would probably be a little bit, here, let me show you a better way to do this one. This is dy dx is equal to 10x minus 2xy, right? Which is what? That's, you know, minus 2x times what? This is actually worthwhile because, you know, I don't really need to use the integrating factor method for this one because while it is in fact a linear differential equation, it fits the right pattern. It's y prime plus py equals to q, right? But I don't need to go through all that because I can do separation of variables instead here. And it's not that hard, is it? I mean, look, if you can see that the algebra here allows us to separate variables, what's the separation? We got dy over y minus 5 equals to minus 2x dx. Integrate both sides, what do we get? Natural log the absolute value of y minus 5 equals to minus x squared plus a constant. And so that gives us that y minus 5 is equal to plus or minus e to the c times e to the minus x squared by the usual algebra, which gives me the solution y is equal to 5 plus like a constant k times e to the minus x squared. So I don't think integrating integrating factor technique is necessary here, so I would shy away from it. Yep.
Why do you always replace the E with C?
Oh, just to make things prettier.
So like if you just left E with C, it's still right.
Yeah. Yeah. But this is a slightly better answer because it at least allows y equals to 5 as an answer by taking k equal to 0. You know, so it's mostly right to leave it as e to the c, but you lose something. That's the other thing. So I again, end up adding back in that extraneous solution by relabeling the constant. It wouldn't be reasonable to suppose that e to the c could be 0. All right, let me try to find one where I cannot separate. How about, this one looks promising. Number 11, which I think I actually assigned for you guys, but I'll work it out with you. X minus 1, I mean, I'm not collecting them, right? Y prime plus y equals to x squared minus 1. 6.5. All right, so remember that the standard form is dy dx plus py equals to q. So I need to get it into that format before I can do that multi-step integration factor method process, right? So what do I got to do? I need to isolate y prime. What do I do? Yeah, divide by the coefficient. So divide by x minus 1. So I get dy dx equals to, dy dx plus 1 over x minus 1 times y equals to x squared minus 1 over x minus 1. Ooh, I see something nice there. Do you guys see it? What's x squared minus 1? Right? So what happens here? Yeah. Assuming x is not equal to 1, right? But if x is equal to 1, this thing is kind of misbehaving anyway, so we're going to pretty much assume x is not equal to 1 throughout here. All right, so what's this is p, right? And apparently q is just this. So we do what? Now our next move is to calculate the integrating factor I. It's the exponential of the integral of p dx, which here is the exponential of the integral of dx over x minus 1. What's that? Natural log of the absolute value of x minus 1, right? Which is going to give me what? Just absolute value of x minus 1. Now let's assume that x is greater than 1 just for the sake of specificity. I try to throw in that condition if that comes up in a problem, because I don't really want us to have to think about the plus and the minus for the absolute value in this context. So if I put x greater than 1, then the absolute value of x minus 1 is just equal to x minus 1, right? although if you think about it, I mean, I don't really need to do that. Well, if you think about it, absolute value of x minus 1 is plus or minus x minus 1. So if you multiply the differential equation by plus or minus x minus 1, either the plus or the minus is going to accomplish the same. Now, let me just say this. I think I have a better way of explaining this. Let's say that this suggests that I equals to x minus 1 will do. Okay, so thinking about it for a minute, I can just drop the absolute value. I mean, the ultimate question is, does it work, right? Multiply by x minus 1. What's that give us? That gives us x minus 1 dy dx, right? Plus what? Plus y, right? Equals x plus 1 times x minus 1. So, of course, the right-hand side simplifies to x squared minus 1 again. And on the other side, we've got the reverse product rule, right? This is, in fact, d dx of what? Of the integrating factor x minus 1 times y. Does that make sense? Going from here to here? But this is equal to x squared minus 1. So at this point, we can integrate both sides, right? Integrate, what does it give us? We get x minus 1 times y is 1/3 x cubed minus x plus a constant. Now I want to solve for y. What's my solution? Y equals 2. 1/3 x cubed minus x plus c divided by x minus 1. There you go. That's the explicit general solution for number 11. Do you guys, anyway, do you agree number 8 was easier to do without finding integrating factor? I think, I mean, if you can separate, it is easier a lot of times. But you can't separate everything. Yeah.
I'm confused about the second part. The second part of blue, where we just have dx and then x subtract with y.
Yeah.
I'm trying to understand. I don't know where that came from.
So this is the, you know, the whole point of the method is that when we multiply by the integrating factor, right? What will happen is the next, after you do that multiplication, what will appear here will be something that if you look at it, it's going to be d dx of I times y, if you did it right. Now, this is I. Of course, this is y. Now, but if we undo that, right, if you just differentiate this, what is the derivative? Well, it's y. Well, I usually do the product rule in the other order, but you know, d dx of x minus 1 times y plus x minus 1 times dy dx, you know? And of course, this is just 1. And it's, you know, that's, so it's the product rule in reverse. This should happen if we calculated the integrating factor right. Let's do another one. Let's try on y prime plus 3y equal to, oh, I think I already did this one. Oops. Let's try y prime minus 3x squared y equal to e to the x cubed. This is number 13. So the first step we don't have to do. It's already in the standard form, y prime plus py equal to q. So this is, p is minus 3x squared. So calculate I exponential integral minus 3x squared dx. That's the exponential of what? Of minus x cubed. So we multiply by I. And that gives us e to the minus x cubed times dy dx minus 3x squared e to the minus x cubed rather, y equals e to the x cubed times e to the minus x cubed. So you guys, you can simplify the right-hand side here, right? It's what? Yeah, it's just 1. And Prince, can you tell me what this is here?
Negative x cubed y.
Yeah, e to the negative x cubed, yeah. See, because the I, again, it's always, if we did it right, it's going to work out to the integrating factor times I being the thing that's differentiated. The reverse product rule step here. Again, you can check by differentiating this and getting back to where we were. I mean, looking for that kind of simplification in an arbitrary calculation is not something we tend to do, but this is not an arbitrary calculation. This is by design, this happens. We multiply by the integrating factor so that the reverse product rule becomes available. So we can see it. And then, of course, that's equal to 1. Integrate both sides. We get e to the minus x cubed y is equal to x plus a constant. So y is equal to x e to the x cubed plus c e to the x cubed. There you go. That's the solution to that one. Let me continue beating this dead horse. Number 14. So here we have dy dx plus the tangent of x times y equal to secant x. I took the liberty of writing the tangent before the y so that it's more apparent that tangent is the p, right? So again, identify this is p, right? So my integrating factor is the exponential of the integral of tangent of x dx. Now that one I'm actually going to have to think about for a second. That's exponential of the integral of sine x dx over cosine x, right? So if I let u equal the cosine, du is what? Minus sine x dx, right? So this is the exponential of the integral of minus du over u, which is the exponential of minus the natural log of the cosine of x. So properties of log, that's exponential of the natural log of the f's value of 1 over cosine x. So we get 1 over f's value cosine x for our integrating factor. And as I've mentioned, the f's value doesn't really concern us, so we can use I equals to 1 over cosine x, and that'll work just fine. Because again, f's value is just plus or minus the function, so multiply by the function, multiply by minus the function. Either way, you're creating the same differential equation. You can just multiply by minus 1 to get the same for both. But anyway, so there's our integrating factor. And so I'm going to continue over here.
And now you can multiply that into your original.
Right. So we got 1 over cosine x dy dx, right? Plus tangent x over cosine x y equals to secant x over cosine x. Now let me rewrite this a little bit more suspiciously. This is secant x times dy dx, right? Plus secant x tangent xy equals to, what's that? Well, that's secant squared. Which is nice because we know integration of secant squared is nothing to be scared of, right? Unless you're a differential equation student who's forgotten all their calculus. And don't be that student. Let's see here. Let's see here. There's still hope for you guys, right? You're in the thick of it. Don't think, oh, this calculus 2 was such a pain. I'm just going to like take a vacation from math and like wait a few semesters to take calculus 3. That would be very foolish. Because it fades, does it not? Isn't half the reason you're in the trouble you're in right now because you took AP calculus your junior year in high school as opposed to your senior year for the sake of getting into colleges? That's what I read in the report. A lot of you guys are taking AP calculus like as juniors. So ostensibly you're not really doing math your senior year of high school, and then you come here and try to take calculus. That's happening to a lot of people. Which is especially bad because that AP calculus course has got like 60% of the material in our calculus course strung out over a year. It's a recipe for trouble. Yeah. So do we agree? Now you see. Okay. All right. And now we can integrate both sides. We integrate, we get secant x, y, right. And so we get y is equal to tangent x plus c divided by secant x. And there you go. There's the explicit general solution. All right, I'm bored of these. Would you guys ask me about something else? Perhaps something from your 6.1 or 6.2 or whatever. 6.3 perhaps. What's that? Power series? You want to start, you want to leave the land of differential equations and start talking about series? I mean, we can do that. We don't have to. I mean, there will definitely be series on the final. I'm not going to sugarcoat it. I mean, that's true. I was trying to devote today for differential equations just to wrap up any questions we have about DEqs today. Yeah.
So the form that it has to be in is dy dx
Right.
equal to
Q, yeah. Right.
And then once it's in that form, then basically we can do any differential equation. with
So then,
that
yeah, we
method.
find I is the exponential of p dx,
Mhm.
multiply
Backwards to the
multiplied by I. That gives us I dy dx plus ip y equals to iq. This will always turn out to be d dx of ip. I'm sorry, iy equal to iq.
because of the integration.
Yeah, because of the construction, because of how we constructed I, it has to have, I is such that di dx is I times p. I mean, so this is going to be di dx. That is inescapable by the construction of I. And then integrate. Iy equal to the integral of iq. And solve for y, yeah. So do you guys have a question about 6.3, a particular one in there? I haven't done a lot with initial conditions. Perhaps we should look at one like that, yeah? How about number 20 looks kind of scary. Here we've got y square root of 1 minus x squared dy dx minus x times the square root of 1 minus y squared equals to 0, such that y of 0 is equal to 1. All right, so we have to solve this initial value problem. I was robbed. That one should win. All right, so I guess, well, one of your hints is this is from before the integrating factor technique section, so it's got to be solved by separation of variables. So I think what you're telling me is I should move this stuff to the other side. Is that? And then divide by thingamabobber? Okay, I guess I'll allow that, I don't know. Yeah, maybe next semester. Let's see here. Unfortunately, I'm not teaching in here, so there's that. But okay, so it looks like we've got y dy divided by the square root of 1 minus y squared equal to, and let's see here. So I kept all my y's on the left-hand side. I'm going to put all my x's on the other side. So on the other side, we got, this is kind of boring. It's like the same integral on both sides, eh? That's funny. Oh yeah, it is kind of symmetrical in x and y, isn't it? So you integrate. I would let this be, let w equal to 1 minus y squared, let u 1 minus x squared. So of course this is the integral of minus 1/2 dw over root w equals to the integral of minus 1/2 du over root u. Let's get rid of these stupid halves. And what's the integral of 1 over root? Oh, maybe I should keep the 2 downstairs. I'm going to keep the 2 downstairs and erase the minus. I kind of like that. See, because then what differentiates to 1 over twice the square root? The square root, right. So this integral is just root w equals root u plus a constant. And in other words, the square root of 1 minus y squared equal to the square root of 1 minus x squared plus a constant. Cancel them. I have 1 on both sides, so I can multiply by -1 or divide by -1. Now, this one's a little bit tricky because we're given y of 0 is 1, right? So you can actually put that in at this point and see what it does, right? So y of 0 is 1. What's that tell me? That tells me square root of 1 minus 1 squared is equal to the square root of 1 minus 0 plus c. So that tells me, in fact, that 0 is equal to 1 plus c. So apparently c is -1. Now, I'm not really done. I mean, if I want to solve for y, there's more algebra I've got to do here, right? Can we solve for y? How should we solve for y? You write it up here. Yeah, square both sides is a good idea. So let's square both sides, just like you said. Don't forget, you gotta sort of, what do you guys say, FOIL things out, you know, distribute. So that's 1 minus x squared minus twice the square root of 1 minus x squared plus 1. So I can solve for y squared. What do I get? Y squared equals 2. Looks to me like x squared plus 2 times the square root of 1 minus x squared, I think -1. So the way I did that, guys, is I canceled the 1 here, and I thought about taking this and putting it over there, right? And I thought about taking these and putting them over there, but then I flipped it around in my head. Anyway, maybe you don't do it in 1 step, but 2 steps. But however many steps it takes, we should hopefully agree that y squared is equal to this, yeah? If I'm wrong, please tell me. I hate making corrections after the fact. So, great. So to solve for y, I've got y is equal to the square root of x squared plus twice the square root of 1 minus x squared minus 1. But to be careful, just a second here, we should put a plus or minus there, right? But if you think about it, we can choose the plus. Why can we choose the plus? We're given y of 0 is 1, right? So if you choose the minus, that makes y of 0 equal to -1, which is not good, because it's supposed to be 1. So we choose the plus. Now, what are you saying something? Oh. Factor? No, there's unfortunately no, and I don't think so. I don't see it right off anyway. So tomorrow, yeah. When what?
What's it called?
Oh, this is the solution. In particular, it's an explicit solution to the initial value problem, which I stated over here. So initial value problem is a differential equation plus some condition. So everything else I've done today, there's been no initial condition. So we had a C in our answer, right? And you've seen that that C appeared in like so many different ways in the answers today, right? It was different in every single one. It was never just plus C either, was it? Not even once today. Yeah. But you know, guys, this whole semester we've been solving differential equations because if you think about it, whenever we calculate the integral of y dx equals to f, it's supposed to be, I mean, suppose we have the integral of f dx equals to y. What's that mean? What equation does y solve? That means that dy dx equals to what? Equals to f of x. See, so every time we do an integration, we're solving a differential equation. We just didn't think of it that way, but in fact, it's been differential equations all semester long. They're just always of this particular type. Yeah. Another way to think about this is the study of differential equations is just advanced integration techniques. So differential equations is more naturally an extension of calculus 2 than anything else. But I think differential equations is easier than calculus 2 because by the time you get to differential equations, you already know algebra, you already know calculus. Hopefully you've gotten somewhat comfortable with them. And differential equations by and large is just applying calculus and algebra you already know to solve differential equations you haven't seen yet. Yeah.
What's your favorite topic in Calc 2?
My favorite topic in Calc 2? That's a good question. I think it's probably the trig substitution. Hyperbolic and trig substitution, yeah. Geometric series are a close second, though. Well, thanks, guys. I will see you tomorrow. We can talk about all the previous tasks. Pretty much it's up to you guys to ask what you want to ask about, okay?